Okay, so we should be streaming. So I got my code books. You got your stuff. Your audio and video is good. Let's do
Yep.
it. Let's just do a quick audio check. Give me a testing. 1, 2, 3.
Testing 5, 6, 7, 8.
Wait a second. I said testing 1, 2, 3. All right. So you're in the yellow. I'm in the yellow. We're looking good. All right. And gotta make sure we are actually online. So let me just do a quick check. And we will get this party started as long as we are. It looks like I'm live on LinkedIn. And let me just double check. YouTube's. I'm getting a lot better with this Restream IO or whatever this thing is called.
Hmm.
Yeah, there we go. And we are live on 3 channels, brother. You ready?
Perfect. I'm ready.
Hey, Felix Sandoval says, just hearing you. Oh, we got the Derek Vigstel in the house, and we got Felix. Man, I'm telling you what, we are going to have some fun. Derek, I was just showing. Hey, Derek, Mike, Mr. King, and I were talking. I got my 1953 code book out. I have my what did I say? My 1897 code book out, because we're going to go back in time. I got my, look at this, Michael, 1923. Look at that.
Wow.
Yeah.
And you know what, Tom? Some believe that you know everything you know because you've been alive this entire time
Yeah,
on one of the Codemation channels, right?
that's exactly right. I'm a vampire. Yep. Bram Stoker's got nothing on me, you know?
Nice.
Yes. So, and I have the 1968 reprint. And I've got the 1971. You know why 1971 reprint's really important, Michael?
I do not.
That's the first time ground fault protection of equipment graced the pages of the National Electrical Code. And that is what we're here talking about. We're here talking about ground fault protection of equipment, commissioning. Hey, we've got Felix Sandoval, and we got Derek Vigstel. He knew I was a vampire. So Mr. King, Mr. Michael King, I know this is your second time with us, right?
It is. It is. And I'm glad to be back.
And I am glad to have you. I would say we, but David is MIA.
Yeah. I think he found out that you invited me back and he just decided not dealing with it and he left, I
I
guess.
know, I
That's
guess.
okay. That's okay.
Yes.
You know what? We can survive. We're
Yeah,
going to, proceed on. We're going to talk about new things and have a good time.
absolutely. And we'll miss him. He's getting his eyes checked right now, so we're all good. So he's all good. So ground fault protection of equipment. Michael, why don't you do this? Why don't you just give everybody a little update on what you do? And I want you to remind everybody of that magic thing that that you're sharing with everybody who uses Eaton Tech Talk.
That's right. That's right. So I am the lead safety and training specialist here with the services group within Eaton. I ultimately started out my career talking about arc flash and doing the analysis and the studies, and progressed through short circuit coordination, harmonic studies, ultimately load flow, transient analysis, etc. Doing all that fun stuff, and at the same time giving a lot of training ultimately, going on site and talking to the end users, the contractors, the consultants that are involved in our system design and operation and maintenance, and gave me a lot of really good experience. Wanted to make sure I got into the field more, so I actually even started going out with our local Pittsburgh, we call it a DOC, a district operations center, ultimately helping them with preventative maintenance on the weekends, giving up my nights ultimately, but that was good. Great learning experience. Loved it the entire time. And ultimately, I ended up here. And for the past roughly 8 years or so, I've been actually with the training group. And that gives me the opportunity to have these discussions with our end customers, with contractors, with consultants, but also our internal employees, from our tech supports the whole way through our field service, our PSC, PSA engineers. And I get to really, have a lot of fun talking about different topics, from panel boards and switchboards and arc flash to grounding. And I changed my background today. Tom, I'm actually sitting in the Pittsburgh Experience Center. I love it. If
I
you go
love
back,
it.
let me back on full screen here, Tom,
Yep,
because
yep.
I really want to point out behind me. Let's see if I can do this right here. On this side of me, right behind me, I have some medium voltage VCBW 15 kV switchgear, and on my right, so looks like left on the screen, I actually have SF6 switchgear that's
Holy
put
cow.
together here in the U.S. Ultimately, yes. So
That's pretty
we're seeing
cool.
we're seeing a huge uptick in the power consumption in a lot of facilities. So data centers are actually loving the SF6 switchgear. 38 kV switchgear, generally about 3 feet across for the breakers in the enclosures. They're down to 24 inches and maybe 18, depending on breaker size. So
Wow.
huge safe space, space savings from that equipment, all because we're using a different insulation, being SF6 gas. So, I really do enjoy my job. I mean, I know I'm sure everybody comes on here and says that, but I actually really do enjoy my job, and talking and dealing with people like yourself, Tom.
That makes a difference. That makes a difference. We got Tamaki Ono. We got Japan in the house. We got Felix Sandoval. We got David Rodriguez. Joseph from Mars. Look, we're not only international, okay, but we are, what do they call that? What's the space? The final frontier, Joseph, the final frontier. And we got Derek in the house. So
I'm glad you went out into space, because I was thinking Mars, PA.
I
But
know.
I think you're right. I think it's the Red Planet. He's there flying the helicopter behind the
Yeah,
scenes for NASA.
absolutely right. Absolutely right. So, and he's on the rover. He's on that rover. Interplanetary. Thank you, Derek. I knew Derek would come up with it. I couldn't figure out what it was. All right. So, Michael, ground fault protection of equipment. We get to see. I know you mentioned this, and I've heard this too. I had a phone call from one of our services guys who was coming back from a job site, and he called me up and he says, he goes, Tom, he says, I'm not feeling right. And I said, why? He goes, I just got off a job site. He had the equipment to do primary current injection testing. He says, and the contractor there, he says, nope, they didn't want him doing all that. He says, I just did secondary current injection testing. And he says, I'm in Ohio, and I know we're on the latest version of the code, which was the previous version, because in 2017, and we'll talk about this, the National Electrical Code started requiring primary current injection testing. And he says, I was prepared to do it. They told me not to do it. He says, I have to fill out a report. But he says, I'm not sure I feel comfortable saying that it's working and that I did what the code said to do, because he knew the code wanted him to do primary current injection testing. So I think that's another good part of this discussion is we've got to cover that, help people understand how it gets done and all that jazz. But
Absolutely. And, we're going to dive into this, but when you look at that injection testing of a ground fault system, it really depends on where you are in the system as to what's required. And that secondary injection testing, if you weren't at the service entrance, that actually suffices the code ultimately. Now, as the owner of the equipment, you could choose to go above and beyond, and that's not necessarily a bad thing to do ultimately to prove your system. Because I mean, coming from the power systems engineering background, doing arc flash studies and coordination studies, I never really got a phone call saying, hey Mike, I'm so glad your breaker tripped. Normally I would get that phone call saying, Mike, your breaker tripped, why did it happen? And we'd have to have that discussion really about, well, the breaker tripped because it thought there was a problem, and if you
yeah,
had that real problem, that's what we want to have.
yeah, we call that shooting the messenger, right? Yeah, that's what happens. Typically, it's nobody wants to hear the news, but that's what happens. But yeah, so we're going to talk about the I want to cover in the code. I want to talk about where it's required, and maybe a little bit of the history on why it was, why it got there, all that good stuff. We'll get into the testing. I know we have some videos, we've got some pictures, we've got some good material that hopefully will help people understand. And I want to talk about the planning. So remember, it's important to understand, and I know you know this as I do, and hopefully a lot of people out there know this as well, that project planning is critical for success. We worry about the qualified person, we worry about all this stuff, but for example, if I land terminals, if I land all my conductors, and then you come out and say, I'm going to have to take them all off again, that's double work, right? You don't want that
Absolutely.
stuff to happen. But this is just a quick overview of the technology, because if you think back in the day, we had breakers that were just big. They were big thermomagnetic circuit breakers, right? The trip
Hmm.
curves, I called those the trip curves of those abrasive breakers. I called that a beer belly, right? Because that thermal overload is real thick, and then you have a real thick bands in there because it's a highly mechanical device. And then that's back when computers were the size of a room, right? And
Hmm.
I think there was a bunch of mice in there running around and all that other good stuff and doing math. They had the little helmets on. And then we came out with microprocessor technology that was able to take the size of a room and move it down to much smaller. I can remember. Well, I can't. I wasn't in the '60s. I mean, I was in the late '60s, not the early '60s. And even in the late '60s, I was more worried about eating and drinking and all those great things that babies do, right? But um, you had that introduction of electronics, and solid state devices start, and really we saw the solid state devices in the relays that were where we would mount the brain in a piece of equipment. We would have the current transformers and the power transformers, and the brain would do some logic and then tell one of those big beasts to open, and it was just like a big switch, right? So when you get into some of the things that were happening, we back then still happen today. We still have rodents. Last time I checked, it's still lightnings. You still get lightning, and I don't think that's globally um, any different. Aging, physical damage. You got conductors that the insulation will age and crack. Chemicals, moisture, all this good stuff. All of these things contribute to a ground fault. And then we have 1971. Hey, we got David Engelhardt. When did the GFPE requirement first get put in the code? Look at this. Look, he asked the question.
Perfect.
Boom, David. It is 1971. This was the code book in 1971. I got a little bit of a pedazzle going on. Okay, it was nice and small. We could carry this in our bags, right? Our tool boxes. But 1971 is when it went in the National Electrical Code, and I've got the preprint version of from 1971 that has, which was gives us the reasoning for why it went in the code. So I'll just read this, Michael, and I'll give you what the language that went in the code is not too far off of where we're at today. Ground fault protection of equipment shall be provided for grounded electrical services. So if it's ungrounded, I don't need it, right? Okay.
Hmm.
Of more than 150 volts to ground, but not exceeding 600 volts phase to phase, for any service disconnecting means rated 1,000 amps or more. So the 1,000 amps went in 1971 from the get-go. And we've
Amazing.
absolutely. And most of the other stuff is pretty much the same. Now, if I look at that's the panel recommendation. Now, the submitter was NEMA, National Electrical Manufacturers Association. And it says the purpose of this proposal is to require ground fault protection of low voltage electrical distribution systems in order to minimize chances of injury of personnel and reduce damage to equipment. And I'll tell you what was going on in 1970 in going into the 70s. I did a lot of research on this because I really wanted to understand what David Englehart's asking. If you look back at some published IEEE papers, Dunkey Jacobs was an author who did some testing, a lot of testing in this area, and he published the effects of arcing ground faults on low voltage system design, because here is what was going on. And he laid it out really nice in this paper. I think it was this paper. Yes. So this is what he's saying is, or what he did say was, that we had a gradual change from ungrounded delta connected three-phase, three-wire low voltage systems to solidly grounded neutral systems serving both three-phase, three-wire, and three-phase, four-wire grounded system. What, Michael, do you know, can you tell us what are some of the issues with ungrounded systems? Why would I not want an ungrounded system? Any ideas?
Well, I mean, ultimately, if you have a true ungrounded system and you have a fault occur, you're going to energize your equipment essentially at that phase voltage, right? I mean, that's a possibility.
Yep.
Now, ultimately means that you have that shock hazard that the user of electrical equipment are now exposed to.
Yep.
And I wasn't. I will admit something. I wasn't alive in 1970 yet, believe it or not. But I'm just going to go back in my family's history and some of the pictures I've seen. I think there are a lot of more electrical devices kind of coming around in that time frame, weren't there?
Yeah, absolutely.
In homes and in commercial buildings.
Yep. And the problems that even some plants were experiencing with ungrounded systems, I look at ungrounded systems like a boat floating in the ocean. When it gets hit with a wave, what happens? That boat goes everywhere, right? So over voltages were common. Unbalanced, or you would have what do you call it? Insulation damage on motors because of the voltage spikes. And when I'm not sure who came up with the idea, and I'm still trying to figure this one out, but somebody had the bright idea to say, I'm going to ground this system. They probably did a corner grounded delta system, right? Because what happens when you have that first fault in a grounded system, in an ungrounded system, it becomes a grounded system. Okay.
Yeah.
So, and then the second fault's always the doozy. So what they were experiencing back in the day, in the 60s, 50s, and 60s, and into the 70s, was a gradual change from going from an ungrounded system to a grounded system. And that means that first fault, to your point, is a doozy. Okay? Now, the other change. Most systems were 208 volts. And then they started to add more loads. They had more load density requirements, and they needed more voltage to begin with to transport, because why do we go to higher voltages, right? We use smaller conductors, lower losses. I can transport power across a campus, and then I bring it down.
Mm-hmm.
So they went from 208 to 480. And what is voltage in a system if I compared it to water? It's pressure, right? So my voltage will push that current, and that creates changes in fault currents, all that good stuff. When my voltage goes up, my currents will come down though, right? Because I have more pressure behind it. So my currents come down. If you think about a transformer, the primary full load amps is less than the secondary full load, as long as the primary is higher voltage than the secondary. So we went from an ungrounded to a grounded system, which means I have higher fault current. I have that first fault current is a doozy, right? There's no gimmies there. I went from a lower voltage to a higher voltage, which means I have more pressure. And then the average service went from 600 amps to 4,000 amps. So because what? The voltage went, the voltage went up, my currents are going down, right? So now I can have, at the higher voltages, I can have larger ampere services, and I transport my power across because of the load density issues going on. And you have the perfect storm for an arc flash.
Yeah.
Right? Because you've got a 4,000 amp breaker, you've got a higher voltage than before, your fault currents are going to be lower because it's a higher voltage. You're into the long time region, you push the instantaneous way over there to the right. And then what we were experiencing in the industry, and I'm going to go back to the substantiation from NEMA when this went in. It said, however, high impedance faults such as arcing to ground are more prevalent than bolted fault currents. In grounded electrical distribution systems, these faults may start phase to phase or phase to ground, because that's what happens, right? And then Dunkey Jacobs showed that it goes three phase. That's why 1584 is only looking at three phase fault currents. And it says the delay greatly increases the risk of injury to personnel. So they're talking about arc flash hurting the people who were getting hurt in these areas. During the past several years, at least 5 major cities have reported major electrical equipment damage, and in 2 instances, fatalities have occurred in which low fault currents have persisted for a sufficient time to cause very extensive damage. And what do we know that does that? Arc flash events, right? So when you look at this, and then you look through Dunkey Jacobs' papers, you have these large overcurrent devices, which you have your arcing ground fault currents, your arcing currents, which we know now 1584 will let us calculate an arcing current. And we know that those lower arcing currents give us longer clearing times. And back in think about the history of electronics. When you're getting into the 70s, Westinghouse, our engineers at Westinghouse were hard at work coming up with ways to address this problem, because that thermomagnetic breaker, those power breakers weren't going to be able to do that, because why? I needed those intentional delays. It's just, because I'm serving all those loads, and they came up with the electronics as a ground fault detection device to let us dial it down for these ground fault currents. And then Dunkey Jacobs in 1986. So after GFPE went in the code in 71, Mr. Jacobs, or Dunkey Jacobs, says, hey, look, in June of 1986, what he showed was that if an arcing line to ground fault is initiated in proximity to 3 bare buses, which what do you have? When you've got a 4,000 amp piece of equipment, you got a lot of bare bus in there. That the hot ionizing gases will cause escalation to an arcing multi-phase fault in about 1 or 2 cycles of time. So in my opinion, when I look at all the history, GFPE was the first arc reduction technology to try to solve a problem at service entrance equipment, because that's where we were seeing burn downs. And ever since then, we've got a lot of testing. We had Stanbeck in 1977 do laboratory tests, and I'm not sure if I have his pictures in there. No, I don't. But he had some really good pictures of where the faults would occur going to the enclosure, and he would show how they would escalate. And I think he did his first, and then Dunkey Jacobs did his testing. And there was a lot of analysis on this, because we created the perfect storm by grounding the systems, increasing the ampere rating of these breakers, and increasing the voltage. Perfect storm. So
absolutely.
And I know Derek Vixtel can go back in the lab and probably get a copy of all this good stuff. And I looked through 1974 and later editions. Ever since then, there's been people trying to modify, and the challenge with ground fault protection of equipment, as you know, and we're going to talk about this. I have 277 volt lighting. I have a problem downstream, and what does it do? It takes out the main, because it's set at a lower setting, right? You've got this little knee coming into these pictures. Now, Joe Bellantoni, the IEEE papers are available, but You would have to purchase them. That's why I can't show the IEEE papers. I can talk about the summation, all that good stuff. I'll put a link. It's called IEEE Explore. Let me just do this for his sake. I'll show you how to get there. You go, I always do IEEE X.
Yeah, it's just X, I believe.
Yeah, XPLORE, and it'll come up, and there it is right there. IEEE XPLORE.IEEE.org. You'll come up with this, and then what you can do is, I think you can just do, if I do GFPE, let's try that. Ground fault protection of equipment. There's 2003. You can look at the dates. So if I wanted to bring this back, that's 1997. I want like what, 1970. We'll say 1970 to 1975. Apply. They didn't do it back then. What did they call that? Ground fault? The escalating ground fault, right? The escalating ground fault. Let's try that. And you can also search by author too. There's your calculating incident energy. This goes to 1977, so that'll be back there. There's 1986. And there's your Donkey Jacobs, the escalating arcing ground fault phenomenon, and you'll see that little red thing. We'll take a look, and there's the reality high resistance grounding. Let's just, I'm curious to see how much they charge for it. A way to PDF, publisher, more like this. I know you can buy it. It's got to be in here somewhere. I don't know.
You might have to click on PDF.
No.
Oh, wait. Go back to PDF.
Yep.
Did I see it there? Purchases or purchase.
Oh, purchase. There it is. Hey, look at that. A non-member is $33. A member is $14.95. So get your IEEE membership, and membership has its value. So, but in any case, you know, the titles that, and you can just go back and pause it and look at the titles and the years if you wanted to ever get one or two of those. I highly would recommend the Donkey Jacobs, anything from Donkey Jacobs back in that time frame. And then the Stein, what is it? I have it in here. Donkey Jacobs, Steinbeck, Stanback, Harris Steinbeck. So anyhow, that's sort of a little bit of the history, just to kick us off on how where it came from. You're welcome, Joseph. And there it is in the 14 code. So this is what we're honing in on, performance testing, right?
Mm-hmm. Yeah, I was going to say one thing I just kind of want to say, Tom, just jumping back a little bit in talking about those time current curves. You know, one thing to remember with the ground fault protection is you're looking at that ground current, right? So, like you said, that's going to be a lesser magnitude of current than what we're looking at for phase, which has its benefits. Because now I can say, hey, anything greater than maybe 800 amps, that's a problem, because typically your grounding conductor should have no current flowing on it, assuming you're in a completely balanced system, which, you know, in my days of being in the field, I don't think I ever found one, but relatively close, right? Maybe you might only have a few amps on it or something like that.
Yep.
But much smaller current we're looking at, and it offers a different way of ultimately coordinating our system, which we're going to talk about in a little bit, I'm sure, is ground fault coordination.
Now, and we know that if you take, and I know I've done this on my channel here. If I don't know what I did with my calculator, but in any case, if you take three angles, if you take three vectors, and we talked about this, if you look back at my symmetrical components or my complex variables little web event, if you take like say 100 at an angle of 120 plus 100 at an angle of 240 plus 100 at an angle of 120, 240, all displaced by 120 degrees. I can't add. If you add all of those up, they'll equal to 0. So all 3 phases, think about it, whatever goes out in all 3 phases, what's coming back, all equal to 0. So we leverage that mathematical, you call it a law of it's a law. It's like a rule. I mean, you can't violate it, right? It's like Ohm's law. It's when they will all add up to 0, and we leverage that for the ground fault. And to your point, what I'm showing here, this is a 4,000 amp circuit breaker with ground fault protection of equipment, and the GFPE is set at 1,200 amps. Okay, so that's a 4,000 amp circuit breaker, and GFPE is set at 1,200 amps. And Kirchhoff's laws, see that? He's the man.
Ryan's got it.
Ryan Jackson's in the house. So I call these curves the hockey stick, right? And that's basically what it looks like. So you have your, there's your 4,000 amp pickup, and then this is down at 1,200 amps, and it's just basically a hockey stick looking at anything that doesn't add up to 0.
Absolutely. And I mean, that is so useful. That's one of the things, when you have a coordination study done, obviously you want all your devices to coordinate from a phase perspective, but also from a ground fault perspective. I think earlier, Tom, and this is probably a good point, time to bring it up. I was talking to you earlier a little bit about the presentation tonight, and you brought up, hey, it's not uncommon to have only one level of ground fault in a system, and how dangerous that can be. And my story, just so everyone knows, is years ago when I was in that role doing the arc flash studies, doing the coordination studies, I'll never forget, I got a phone call from a very upset customer of mine, and the consultant engineer was on the phone, and the contractor's on the phone, and all these people. And ultimately, I determined their settings. So, when the breaker tripped, it's obviously my fault. I get that. And what I remember is it was actually a cancer treatment center. So, a facility you don't want to take down when it's actually operating. And the contractor was doing work in the wall that also had the gift shop against it. And the contractor actually put a saw blade right through that cable, right? So it's just a simple receptacle circuit. Downstream in the system, that ground fault current obviously flowed the whole way back up through the main device, their only level of ground fault protection. And sure enough, took the entire cancer treatment center offline temporarily. So, it's really important to think through all these things, right?
Ouch.
Not just, I mean, not what do we buy, but what do we buy? How do we maintain it? What are all the other considerations for the system?
Yeah, and you think about, the National Electrical Code requires in 23095, right? So in 23095, this is the 14 code. Let me look at the 20 code. So in 23095, you're required to have ground fault protection of equipment. That's just the testing. So you have to have any of your, if it's a grounded system, if it's grounded and with the right voltages. I'm just going to look at the.
I was going to say, I got it right here, Tom. I got 150 volts to 1,000 volts, phase to phase, and 1,000 amperes.
Right. So we really narrowed it down to grounded. Why? Because back in the 60s and 70s, because of history, we knew we went from ungrounded to grounded. So they weren't worried about ungrounded systems because they weren't having problems. They weren't having this issue. They went to grounded systems, and then they said they knew the voltage, and then they knew it was the large overcurrent protective devices because they had the history in the smaller overcurrent devices. They were going to the larger, had those high instantaneous pickups, and so they settled on that 1,000 amps number, and it's stuck there ever since. But I'll tell you, so if I look at, I'm just giving you an example from the 14 code from the performance testing. They added primary current injection testing, and then the important thing is that they in the 2023 cycle, this is what I was looking for. They're moving. The thought process is panel 10 is going to take the 1,000 amps down to 800 amps, and this will be the first move that that this section is seen since 1971. And you know why? Here's what happens. And you know this, right? 1,000 amps. If I want to avoid GFPE, what do I do?
800 amp service all day long.
All day long. Or I'll do two, two smaller amp. I'll put two overcurrent protected devices. So here's the issue. The National Electrical Code is going to be eliminating, or has in the 2020 code, you can't have a panel board now that has 6 disconnects. Why would I have done that? I would have taken a panel board with maybe 400 amp breakers instead of one 1200 amp or one 1600 amp breaker, because I don't have to do GFPE, right? It lowers the technology that's in my service engine's equipment. I can have up to 6 disconnects in one panel board. Now all of a sudden, I can't do that anymore. And I have to either have a main in there, or I have to have like a disconnect switch or something like that. So they're making it harder to get around these types of requirements, and they're lowering it because of issues that we're seeing in the field. We're still seeing arc flash events. We're still seeing burn downs and events at service entrance equipment and other areas in the distribution system. So this is going to be a big change. And I think the changes that we saw in service entrance equipment, removing the 6 disconnect, or changing the 6 disconnect rule, removing the permission of 6 disconnects in the same panel board, is going to facilitate probably a lot more GFPE and more arc reduction technologies at 1200 amps. Because what we're doing with that, the 2023 is looking at taking 1200 amps and moving it down to 1,000.
Yeah.
So you got GFPE moving from 1,000 to 800 for the 2023 code cycle. You've got arc reduction technologies going from 1,200 down to 1,000 amps. So you're seeing there's a reality that it's not about the size, technically about the size of the service. It's about the clearing time of the overcurrent protected device with respect to the currents that are flowing, whether it be a ground fault current or an arcing current.
Yeah, I mean, I think it's really about, like you said, the protection of the system, right? And I think this is a natural progression, right? The technology we use today is better than in 1971, as the example,
Yeah.
right? So as technology is getting better and better, I see that this continuation is going to be there of, okay, let's put more and more protection on our systems. Because I mean, you and I both know, we both attend, as an example, the IEEE Electrical Safety Workshop. We attend safety conferences, and we've made this industry better. We've made it safer. But you and I both know there's still accidents occurring, right? There's still shocks, there's still arc flashes occurring. And I think as the technology gets better and better, we're going to put more and more protection features into the systems. They're going to be required by code, and we're going to continue to lower those numbers.
Absolutely. And a lot of people, from a performance testing perspective now, so we had this discussion, and you'll notice that 24087 and 24067 in the National Electrical Code this 2020 cycle included performance testing of those solutions, which I think we have to keep that in mind, because what we're talking about, performance testing on installation of ground fault protection of equipment at 1,000 amps and above. And if you're above 1,000 amps, if you're at 1,200 amps and more, then you have both GFPE performance testing and arc reduction technology performance testing. And sometimes you can kill both with one stone. And you got to make sure you plan it correctly. So what is often missed, and we've lived with years with this performance testing, saying that testing shall be conducted in accordance with instructions provided with the equipment, right? And then in the 17 code, it said that you have to be a qualified person and using a test process, not off of, geez, I can't spell, of, yeah. Here's how we fix that. You ready? Watch this. Watch. Abracadabra. How'd you like that, huh?
That was awesome.
No, watch.
Awesome.
No, watch. Abracadabra, and it's back.
Abracadabra. Tom, I think everybody out there is going to now think that you already had the slide prepared with the typo, and you're just advancing next slide, back,
Oh,
advance, back, advance, back, right? They don't know the magic you just had to perform live
right. That's
on
right.
this tech. That's amazing.
It's amazing. I'm telling you. So so now in as part of the 2017 code, you have to do primary current injection. And that was the phone call that I got from one of our services guys who said, "Hey, I know," and this was in Ohio, I believe it was, and they were on the 17 code, and he said, "I know this is a code requirement here, but," and he knew the contractor. The contractor didn't realize. He tried to educate the contractor, but you know who at the end of the day caught all of that? The electrical inspector, because I think it was a he looked at the test and he said, "Well, you have marked down here secondary current injection testing because that's this report is all saying, and the 2017 code says you have to do primary current injection testing." And then my guy called me back up again. He says, "Guess where I'm going today?" I said, "Where?" He says, "Back out to that job site." Right. So that was 2 visits, and think about all of those wires were terminated. They had to unterminate stuff for him to get his test leads in there. He had to establish electrically safe work conditions. He had to bring his equipment in and everything else associated with getting that job done. And that's expensive and time consuming.
Absolutely, and I'm sure that that was not just 1,000 amp service
No,
entries,
it
right?
wasn't. That's right.
There we had 3 sets of 500 MCM landed at the
Yep.
primary side. Now that was probably a 4,000 amp service where you have
Yep.
10 sets per phase to disconnect
Nothing's
and
easy.
work around. No, not easy at all.
No.
That was probably a multi-day job, right? By the time
Yep.
you just created the electrically safe work condition, you disconnected everything, did your testing with a primary injection test set, or as you call it, the Phoenix.
Oh, the
Right?
Phoenix.
Oh, we gotta get to the Phoenix here, and then you had to put it all back together.
That is
I mean,
exactly
that is
right.
not easy.
No, it is not easy. And when we say the Phoenix, right? So we're talking the Phoenix, right? So and this test setup, and I think I even have I do have a video. I'll just play that one real quick. Let me make sure it's muted. But this is this is in a controlled environment, and he's testing this. I guess that it looks like a Magnum power circuit breaker. It's probably not an insulated case, but I know some of those they look so similar. But he's going to he sets those settings, and then here we go. So I just want to find where he's actually moving that breaker. So he'll do the settings, and then he'll take it and he'll say, "Okay, now we're going to do a different what do you call it? A different phase of the breaker, a
Yep.
different pole, right?"
Yep.
He rearranges all of his leads. And now this equipment, look at the size of the equipment. I don't know how much that thing weighs, but now, and then he pushes that on. Now he's not wearing any PPE. Why isn't he wearing any PPE? What he doesn't have gloves on? What gives, Michael?
So the big thing about a primary injection test set is while you are pushing out that high current, there's actually no voltage driving that current. So I know a lot of our customers are concerned about primary injection because when you look at breaker manuals and you read the instructions, which some of us occasionally do, you find out it's only and read the standards. They're only made to interrupt a few faults at the high currents, right?
Right?
Before need to be serviced ultimately, because you're going to burn off contact material and all that kind of stuff happens behind the scenes. In a primary injection test set, you're pushing the current, but there's actually no voltage. So the power that's actually going through the breakers actually not that great ultimately.
Yep.
So that's generally why you're not seeing the use of gloves and all the shock protection. But you were saying about how much it weighs. That test set is probably easily 1,000 pounds
Yeah.
that you're taking to your equipment, right? And in this environment, we're just testing a breaker. In the real world, I'm going to do air quotes here, the real world, what you see is we're having to disconnect those cables from the transformer. and maybe they're just a braided cable, so that's relatively easy. And we're going to attach cables to the output of this test set and wire those 500 MCM cables, 750 MCM, etc., into the gear to do the test. And then we didn't even talk about where does the test set get its power from.
Yeah.
That that's a three-phase test set power coming in.
That's
So that
true.
could be 208, 480 volts, needs a 400 amp service. Now you're at your facility, right? You're
Yeah.
down because well, you're just building this facility. You don't have utility yet. How do you get the power? Now you're renting a generator to run the test set.
Wow, I never thought about that. You're right. You're right.
The planning that goes into this is not just something we just say, hey, we're going to show up tomorrow to do this test. It doesn't work that way.
Yeah.
A lot of planning.
No, that's a very you know what? And I never thought about that. That that's a good point. That is a really good point. And to your, so you got to get now there are other sets of equipment. You don't need the Phoenix, right? You could use other types of test sets that aren't as large. And I guess what really determines the set that you're using is the type of test you're doing, how much current that you need, right?
Absolutely. Yep.
Yeah.
And this isn't the biggest one they make, but it's not the smallest one either. It's kind of in the middle of the road ultimately that they make.
Wow.
Uh,
And you know what this is? This is
and,
a
and I should say, just so I point out to everybody, Tom, when you say the Phoenix, they spelled Phoenix wrong, right?
I noticed that. You know, that is such a good point because I mean, they forgot the O. I was surprised at that, but in any case, I mean, you know, you look at these, and I mean, another thing to consider too. I mean, this is a nice shot of the back of this breaker and some of the mechanisms and stuff, and why maintenance is so important. You know, these devices are I call them Swiss watches of our power distribution systems, right? Because they're so complicated and so complex. There's so many small little items and screws in there. And David Engelhardt said, "I got Jimmy Dollar doing this," but that's not Jimmy, David. Now he said he heard of a manufacturer requiring the utility connection to conduct the initial test. That's interesting.
Mm.
So I'm now that's interesting, David. I've not heard that one before. I've not heard that one before. I wonder. Yeah. Now, Mike,
Yeah, so requiring maybe a temporary feed from the utility or,
it could be.
to
Well,
be that entrance.
to your point, though, it could have been that that whoever was doing it did not have the generator to be able to power some of the test equipment.
Yeah.
Yeah, and I never thought about that, but that is so true. I mean, this piece of equipment needs power.
Mhm.
Hmm.
Yeah, and really, I mean, if you go back through history, I mean, and let's talk just breaker testing in general terms here. When we had our series trip devices years and years ago, right, like decades ago, every device was primary injection tested, right? That
Right.
was your only option to test it. Then, as you showed your time frame, your time chart there,
Yeah.
right, timeline, you saw like 1970-ish or so, somewhere in that time frame, we started talking about microprocessor-based devices were
Right.
coming in. Ultimately, that's when we kind of switched over to secondary injection, and really the thought process there is how often does a CT or a sensor in a breaker, how often do they fail? How often does the wiring actually on that circuit fail internal to the breaker? It's not common. It
Right.
happens, but not real common. So, we've kind of said, hey, let's use these other injection test sets. They work really great ultimately, but they kind of miss some of the testing, and that's why when we look at, I think, the National Electric Code requirement for this ground fault testing, it's when it's first installed.
Yeah.
We're making sure that the system from the CTs through all that wiring into the breaker, which we haven't even talked about. Okay, what happens when you have main tie mains and you're doing residual,
Yeah.
ground fault protection and all that kind of stuff? How you have multiple CTs now, and ultimately, if you did secondary injection, you're missing all of that circuitry. Now the code is saying, well, no, wait, you need to go test that in your system, make sure it works. Beyond that, then you can just do the secondary injection.
That's right.
Perfectly acceptable. But that first install, that first test, we need to make sure all that other stuff, not just the trip unit, is working properly.
Yep. So let's talk about all the different components in the system. I know you have the relay itself, and in some cases, the CT and the relay are all part of the circuit breaker itself, right?
Yep,
But
could be.
not in all cases. So, and what I'm showing here is a Y grounded system. So this will be your typical system. And I noticed that in this case, there's a CT in the ground, going to ground. So you're actually monitoring the grounding electrode conductor, basically going to the ground.
Yes. Yep. Yeah, and we're making sure that there's no current flow there ultimately.
Yeah.
And that's really what we're looking for, is that current flow. Because what you're missing in this diagram is, if you imagined out where that box is that says to pull 4-wire load, if you had a fault there and you drew a little ground symbol there, that current, that phase current from phase A, B, or C, would actually flow down into ground, and then it would come back up through that grounding conductor,
That's right.
through that CT, that sensor, and go back to the neutral point on the source itself, which could be a generator, could be a transformer.
Yep.
Ultimately.
So
And that's what we're looking for, that unusual path.
so what happens here is this is one method, right? Where you have a ground fault relay that's in that ground. Another method would be to use a zero sequence CT, because we know that A, B, C, and neutral, you would not put your equipment grounding conductor through that donut, right?
Mhm.
We know that A, B, C, and neutral all should add to 0. And if I see anything, obviously with errors and margins, right? When I see currents greater than 0 or greater than a threshold of number, then I know I've got a ground fault out there, and I open up.
Yep, absolutely. And I want to say that first one, I forget what your slide just said, what the title was on the last slide. So the ground return or ground fault detection, another name would be source ground.
Source
Is
ground.
another term on the manual, source ground.
Okay, perfect.
Measure ground directly.
Let's say that again.
So we're actually measuring the ground current directly, basically, right?
Right.
Versus zero sequence, on your second slide there, we're not actually measuring current in the ground path.
Mhm.
We're doing that summation. We're doing a calculation of what it is. We're not actually measuring it, though.
Right, because you're relying on physics with all of the fields canceling out with each other.
Yes.
Yep. And then the third is the residual current. So this is when you're putting CTs in each of these and then summing that separately, right?
Yes. Yeah. So zero sequence and residual are both working off that summation principle. They're just coming to the summation in a different way. The zero sequence is one CT. So think about the magnetic fields of all those wires. Magnetically, they cancel out, so you don't get any magnetic field in the iron core of the CT, which then
Right.
would go over to the secondary wires. Versus residual, every wire is going to have that magnetic flux going through the CT. It's going to have secondary current, and then we sum the secondary current.
Right.
Same principle, just different way of measuring it.
Okay, so let me ask you a question. When you test this system versus this system versus this system, would you test it differently?
Yes, you would. I mean, you have to, right? Because in the source ground scenario, you need to actually have current flow through that ground CT. That's what you're really testing versus the zero sequence and residual. You need to make sure you run current through the multiple CTs or the summation of the CT in opposite directions, because a lot of people forget when we're testing this, we want to also make sure that in certain scenarios it doesn't trip, right? We want to make sure all the polarity of all the devices is all correct when we do this. So the testing sequence is a little different depending on what system you're using. And you could end up doing just maybe a handful of tests, maybe 4 tests, or I think one of the charts here I have, I think it was 18 different tests
Wow.
to confirm your ground fault's working properly. The testing sequence is
Wow. Wow. So I got now I'm gonna get to Bill Neitzel, but we got one. It just says LinkedIn user. It looks like he or she loves residual versus zero sequence. So looks like we got a thumbs up on residual. I think it's Douglas Strang. Yeah, that's why I called up my. For some reason, the this Restream IO for LinkedIn doesn't give me some information. So that was Douglas. Thank you, Douglas. Now I see that Bill Neitzel says he ran across a school built in the mid 80s, 480 volt, 1000 amp fused disconnect to a an MDP breakers, no GFP protection. Okay, so my thoughts and fixes. So if you have now, remember, well, late 80s, so that would still need to have ground fault protection of equipment. So somebody missed it. If it's a fusible equipment at 1000 amps, because it's fusible switch, it presents some unique challenges. Even if it was a circuit breaker, you're going to have to change the breaker out. In that case, you think about how we do this on fusible equipment. We use stuff like this, which is a relay, right? And this relay will shunt trip the switch. It doesn't tell the fuse to open. It basically tells the switch to open, but your switch has to be mechanically able to open based upon a control voltage or some sort of control. If your switch itself isn't able to do that, then that just it complicates the situation. But I would always go back to the manufacturer and say, look, if you want ground fault protection of equipment on that school that's built in the 80s, late 80s, I was in high school or going into college. Actually, I was going into college. You're going to have to, you might have to change some equipment out. Yeah.
Yeah, I would just say the other thought I might have is playing to the hearts of the local utility that it is a school and we care about our children, right? We want our children to be safe. I mean, Tom, you know me, I'm a newer father. I have some younger children, and I do things differently in my house now than
Right.
maybe 7 years ago. I would potentially ask the utility what their upstream devices maybe on the primary side. This is a single service to that school. Potentially, you might be able to work something out with the utility where you sense ground fault and you trip their device. I don't know if that's really code by
No,
use
you
their
could do that. You could.
right. I mean, it doesn't say it has to be the service entrance device on your side. It could be the utility side.
Yeah, you would have to install some CTs somewhere downstream, right, to sense that ground fault, and then you would have to shunt trip something. But so Bill says they're looking at replacing the equipment, which I think that's really where you're going to be at, Bill. And sometimes it's hard to bear that news to somebody to say, look, but if you think of it, it was late 80s. There's new technology, and if it's a school, I would suggest if whatever they put in, put some metering in so that they can get some other valuable information for the school, energy load profiles and things of that nature. So I would look at new technology that's on from a safety perspective and from a perspective of can I help improve maybe some of the energy usage in the facility or whatnot. So you can make it safer, you can make it more reliable, and you can make it more efficient. Sometimes depends on what you're doing and what you're changing
Mhm.
out. So
Yeah.
so residual versus zero versus monitoring that return, are all three of those are different methods to achieve the same goal, and they would all be tested differently. And then, so this is just a slide that just talks about what you explained. You have all the current going through this CT, it's coming back. So as long as all your currents stay in the conductors that are going through that circle, which would be the current transformer, then you know everything's covacevic. It all adds up to zero. But the moment it goes outside of that path and finds its way back to the equipment grounding conductor, that's when we say all heck breaks loose, right? So when it does something like this, it's bypassing the zero sequence CT, and you'll notice it goes right into that grounding electrode up through the your what do you call that? The grounding electrode conductor, your GEC, and it's just one big circle. So this would be a separately derived system, because it's all derived from that source. This is the source, and currents will find their way back home, and they circulate. They don't go home to the utility. It's not like they say, "Oh, I'm gonna just go right back to the utility." They go back to these separately derived systems that you've established with that grounding electrode conductor and the grounding electrode, all that good stuff, and your currents will circulate there.
Yeah, I was just saying, in talking about, I think this is actually a great thing I just thought of as we were looking at this chart here. You were talking earlier about the time delays we put in the phase protection, right?
Yeah.
And we do that in the ground protection also. But I mean, how resistive is this fault when you think of it literally traveling through earth, right?
Yeah.
Through ground. Maybe your facility's cement, dry cement is actually a relatively decent insulator, honestly. So this fault current might not be of the magnitude that the phase protection ever even sees it. It may be below that phase protection, or it may take hours for the phase protection to operate. Goes back to your fires.
And you know what? And I don't know if my buddy Ryan Jackson is still on the line, but here's 250, Article 250, 122. And Ryan, I liked your video. He did a video on 250.122, and I have a theory, because what you just said is what is so perfect, because 251.22, and I don't know, Michael, if you even know what that is, but I'm going to tell you what it is. There's a section in here that says, when you increase the phase conductors because of voltage drop, right? Okay, say I've got a very long run and I increase my phase conductors because of voltage drop. What I have to do is increase my equipment grounding conductor proportionally the same. Okay, and I'll tell you, this was a while ago. I scratched my head and said, "Why? I don't get it. Why would I have to increase my equipment grounding conductor?" I mean, from an engineering perspective, I'm like, why? Right? So, and I asked people on Code Panel 5. I asked Chuck Mello. I talked to Vince Saporita, and you know what? I got two basic answers. One was, and I had a very astute gentleman who pulled me on the side, put his arm around my shoulder, and he says, "Thomas," he says, "don't you know that when you increase the length of a conductor, you're increasing the impedance, and the fault currents will be very low?" I said, "Yes." He says, "And what happens when you increase the size of that conductor? What happens to the impedance?" I said, "The impedance will go down." Right. He goes, "And what happens to the fault current?" I says, "Yeah, well, it will go up." He says, "That's why you have more fault current going through the equipment grounding conductor, and you need to make sure you protect it." I'm like, but if I shorten the conductor, I can get more current to flow through it than a long run where I'm just changing the size. If I want to increase the amount of current flowing through a grounding electrode conductor or equipment grounding conductor, I shorten it up. I make it 10 foot instead of 100 foot, and I'll drive a lot more current through the equipment grounding conductor. And then I was told to go read Source Grounding book. So then I talked to another individual, and they said it has nothing to do with fault current flowing through the equipment grounding conductor. This gentleman's on panel 5. He says it's all about the fact that you're going to have a low fault current, and you won't trip the overcurrent protective device. And I said, well, that's why I will have ground fault protection of equipment, because of what you just said. When I have a fault current that is lower, I mean, I'm not required anywhere in the code to have a fault current greater than the long time pickup or short time pickup or in the instantaneous. All I have to do is protect the conductor, which we do with overcurrent protection. And we know overloads can exist. I'm not going to damage the insulation. So David Engelhardt, the equipment grounding needs to increase for voltage drop. The current gets back to the source to operate the overcurrent protected device. So and that's what I'm getting. And I'm like, it doesn't make sense. My overcurrent device will operate. Okay, think about it. If I have a 200 amp breaker, my ground fault current would have to be less than 200 amps for it not to operate.
Mm-hmm.
And that's going to be a huge run. So I did all the math. And oh, by the way, the equipment grounding conductor is a bare copper conductor with no insulation. Okay, I'm going to protect the phase conductors, which have rubber or some conductor coating, which is probably going to melt well before the copper does. If I protect that from overloads, I sure as heck am going to protect my equipment grounding conductor. So then I had someone else tell me, well, Tom, you want to remove it because of shock hazards. And I said, well, grounding doesn't prevent shock because ground currents will find every way back. So I have yet to hear a logical, engineering-based, factual-based reason to increase the equipment grounding conductor size on a long run. Because I said, look, when I have a long run, there's nothing in the code that says that I have to have a certain voltage drop. I mean, they talk about voltage drop in one area in the National Electrical Code. But if I don't increase the conductor size, my fault current will be even less because I have more impedance. I don't have to do anything. If I do increase it, then I have to provide it just does. I have yet to find anybody who can explain why and show me the fact. So then what I did in the code, I put a public input in, not to remove it. What I said was, if I provide ground fault protection of equipment, I'm now providing protection of that equipment grounding conductor at a lower value below the long time pickup, right? I got the hockey stick going on and we just looked at it. And what they did in the 250.122 for the 2020 code, they resolved mine, but they gave me a carrot, which it already existed. There's an informational note, there's an exception. And it says equipment grounding conductors shall be permitted to be sized by a qualified person to provide an effective ground fault current path in accordance with 250.4A5 or B4. So if you go to 250.4, and I know this is taking me down a different path, but I'll tell you what, this is something that I think ground fault protection of equipment, because what it goes with here, if I provide ground fault protection of equipment closer to my load, I can take a fault off very fast. I will coordinate with that fault that's required, the ground fault requirements on 230, right, at the service sign threads. I can coordinate now with that and provide coordination, not do what happened to you in the cancer center, right?
Yep.
And I know other electricians who have told me about the stories of, well, I had this and I took the main out and they couldn't figure out why it tripped the main and not the smaller breaker that was feeding. And it was because the current was so low because of the ground fault current and the impedance in the path. It was so low it did not trip the device that was feeding it, but it tripped the ground fault protection, which if you had it closer, you would have taken off of a branch circuit instead of a main.
Absolutely. I was just saying, Tom, you just made me think of another issue and another example in my history. There's a high school right here in Pittsburgh
Mm-hmm.
that I won't even discuss their name. I'm not going to say their name, but I got called out there to do some power quality measurements years and years ago because they didn't understand why their ground fault at the main device was tripping and they couldn't figure it out. And I actually was able to capture some ground current that would increase, and sure enough, then it would trip. And they would turn it back on, it would increase, and it would trip. And this would happen. It took some time, but ultimately, what was causing all their issues, and after doing a lot of investigation over months of time, we figured out that every single time their ground fault tripped, they needed to change the lighting ballast in the gymnasium because one of the lighting ballasts would fail. It would resistively short to ground
Oh,
and
wow.
cause just enough current that over time that current would start to increase until it got it to the level where it would trip. But lights in a gymnasium, they go out. It's 30 feet up in the air, 40 feet up in the air. You don't go change a light bulb on that, right?
That's
You wait
right.
till like 6 or 7 of them are out, right? And they didn't know that they had this issue.
Wow.
Talking about another example, and you got my mind going here. I was just out of town a few weeks ago at a chemical plant, and they had installed brand new switchgear with a high resistance grounding detection system in it.
Ah,
And in the system, they purchased all the bells and whistles. So they had the indicating lamps on it to tell you which phase the ground fault was actually on. And how that system works is your three lights are normally on. That means you have no ground fault. If one light goes out, that's the phase
right.
that you have a ground fault on, right? The light was just dim. And we looked at the amp meter that wasn't a true amp meter telling you amperage, but instead it told you your system's good versus you have a low resistance fault. And based on people's experience, I'm assuming they were drawing about half of an amp of ground
Wow.
current, and that was making the one phase look a little dimmer. The system had actually activated saying they had a fault somewhere in the system, but we're talking like half an amp.
Wow.
So these ground faults aren't necessarily these big events that we think of. I mean, it happens for sure, but a lot of times they're just very, very small events that just kind of sit there and that current just flows and flows and flows.
Absolutely.
And current through a resistor, as you've said, it's heating, right?
Absolutely. That's right.
Right? You gotta burn that power somehow. It's heat, and that's going to cause your facility to essentially burn down over time.
Absolutely right. All
It
right.
all ties together. I love it.
Absolutely. It all ties together. So we covered these three things, right? Zero sequence, source ground, and residual.
Yep.
We talked about these are the different components, the grounding electrode conductor, and how it's wired makes a difference. These are different types of CTs. So you got your Windows CT, your bushing CTs, and now on these, what you would do is verify the turns ratio, right?
Yep.
And how do they do that? How do we determine the phase ratio? You
So, so number one, we'd be looking at the nameplate, right? There's
right?
going to be a nameplate on here that's going to tell you the ratio. Now, if you go back into the old days, it was painted on or written with a marker, so you probably can't see it anymore. But as part of start commissioning maintenance, any transformer, we should be doing a turns ratio test. And that's actually a very simple little test. A lot of them are handheld nowadays. Connect your leads on, hit go, and it will actually tell you everything you want to know about that CT. It's just a transformer. It'll tell you the turns ratio, the resistance, is it
Nice.
subtractive, is it additive, all that good information.
Excellent. So it's an easy test to do. You got to get the right, and sometimes the CTs are not marked correctly. So you got to verify that, make sure it's marked correctly, all that good stuff. This is just a picture of a zero sequence CT that's mounted and actually it should be up above, but it's mounted down below. It should be up above it. It'll depend upon your source, where your source conductors are coming from. If they're fed from the bottom or if they're fed from the top, obviously you want the CTs on the line side of the fusible switch. And in this case, we had to move that CT up. And George, that's okay, George. George, you're a little bit late. So is you're joining Chris Follen. You guys were probably both at the same meeting, and then we got Bill Neitzel flying in the air, heading out. All right. So, where do you want to take it now? Let's talk about the testing. What do you think? What do you want to talk about now?
I think we should talk about the testing a little bit, honestly, and from the perspective of you know, they're wired differently, right? And we got to figure out how do you actually test your ground fault system to meet the code requirement that we've been talking about here.
Right. Right. So, I'm going to go back to some of your slides. You've got what's this one here? So this is a Digitrip 520.
Yeah. So source ground. So what you see there is you see your phase CTs, right, on the top where it says like R/1. Those would be your phase CTs, and then you have that source ground CT that you're highlighting down there in the bottom left-hand corner, B4 to B5 on that trip unit. That's the actual CT that's going to be on that grounding electrode to measure ground current. Now, I believe, and let me just read my notes here. Yes, in this instance, there's that jumper B7 to B6. That's how the trip unit actually knows that that's how you're measuring ground fault current. So when we talk about testing of the system, it's not just confirming that CT ratio. It's not just confirming that when you inject current through the CT, it goes into the trip unit. You're confirming the settings in some breaker types, some trip units or relays, but there could also be jumpers that need to be installed. And I mean, anybody that has looked at these trip units or looked at the backup relays, some of those jumpers are very small. I was actually, it's interesting. We actually have a relay testing class in Warrendale, like right now happening this week.
Oh, wow.
And it's awesome to have some in-person training taking place back here in the facility, an internal class. But ultimately, we're testing relays, and they were actually trying to test zone selective interlocking, completely different, right?
Oh, yeah.
But, right, they're testing it, and they're saying, I just happened to walk in the room. They said, Mike, this isn't working. We know that you're a smart guy. Can you help us out? I was dumbfounded. I couldn't figure out what they were doing wrong. And then the one gentleman turned the relay around, and he looked at the screws. He says, oh, there's actually a jumper right here. I didn't even see it because it's a small little jumper. So very easy to miss those. And that's why we want to do the test, because we're human. We make mistakes. We miss jumpers, put jumpers where they don't belong. We want to confirm that.
Yeah. So now in this case here, it's a Digitrip 520, and we're showing the trip unit, but that trip unit is in a circuit breaker. So the CTs that we're showing, the CTs that we are showing right here, and here are all a part of the circuit breaker, right? That's all built into the circuit breaker. Now, and I've heard some, I know, like we make these circuit breakers up in our Beaver facility and other facilities here in the United States, right? So, and I know we put them in test beds and we test all these things, but that doesn't guarantee that one or so doesn't get out that doesn't have the right CT and the right polarity. We have test records and whatnot that you can get that shows that, because you never know. I mean, if something gets shipped and somebody changes something, because some of these are power breakers, you can take these apart, you can do different things to them and maintain them. It might not be what it was when it left the facility, all that great. There's a lot of different reasons why a sensor might be in the wrong way. But testing those sensors, because we'll do the standard testing just to make sure you'll do a phase A, B, and C test in addition to the ground fault protection, because you want to kill all those birds with the same stone. If you're bringing the Phoenix out, use it and run the test through. You have a very low voltage pushing current, you can push enough to trip each one of these poles and test each one of those to make sure that everything is working correctly. Just do it. So,
Mhm. Well, and also, Tom, like you said, those CTs, those sensors for the phases are in the breaker.
yes,
That ground CT is separate, so it's in the back of the switchgear, or maybe in the next section over. Right, we have a cable compartment that it's mounted in, and now how did you get from that section through into the next section
that's right.
over, from the back of the gear into the front of the gear? All it takes is one wire to be misplaced, or even sometimes a loose wire, right? One
Ah,
terminal just came loose during shipping,
that's right.
and now it doesn't work.
That's right. Absolutely right. And now this is your zero sequence CT, right?
Hmm.
And
So typically, current, from phase A there, the black arrows flows through the load, comes back on neutral for a single phase load. Ultimately, the current flowing right equals the current flowing left. So the summation becomes zero. When you have a fault, though, you have this other path represented by those red arrows on the bottom through that ground, and that's what's going to be that ground fault
right.
ultimately.
Yep. And now, so let me ask you a question. Do you have to pull the breaker out to test it? Can you test it while the breaker is in the equipment?
So if we're testing the complete system per the code requirement for the first install test, the breaker needs to be racked into the gear. It needs to be in its normal operating state.
Yep.
So we're flowing current through your phase sensors, right? Through the breaker and then back out. We need to test it, two tests here, really, right? Phase A, the normal situation where
Yep.
we should have no trip. And then we need to take the current around that neutral conductor, right? Through another path outside of the sensor and confirm that it does trip appropriately.
Right. So,
Um,
so,
so, so
so you really are, you're going to be in the equipment. You're going to be clamping things to inject current in certain areas of that bus. Um, do you have to isolate anything else? I mean, do I have to make sure that I don't have, I don't know, is there anything I have to think about outside of that box?
so you need to think about, are there any other paths
Yeah,
that you're not, necessarily considering? So, generally you would open all of your feeder breakers just to ensure that that phase current doesn't actually go somewhere else and come back through a typical, other path
gotcha.
ultimately.
Okay, okay.
Now once you've done this first install, the code doesn't have a requirement for the primary injection testing later on, right? It's
That's right.
only for this first install of the whole system. So typically, what we see is after you do this test for first install, every test after that, you could do primary injection. And at that point, it would be a lot easier to just pull the breaker out and just test the brains, the trip unit of that breaker, right? Or your relays, etc. Or you could ultimately go to secondary injection testing or functional testing. Those are all acceptable per code right now.
Right, because what you've done on the installation, you've confirmed the CTs, you've confirmed the wiring, all those jumpers that you talked about, and since it's in there and working and functioning for 3 years or whatever, however long you've got it going on, and eventually you say, look, I'm going to make sure that the brain is still working in this breaker, and you're going to be testing the basic functionality. You're going to be opening it, closing it. You're going to be doing all of those functional things from a lubrication perspective and all of that. You don't necessarily have to reprove that the CTs on the bus are the have the CT ratio that you need and are right polarity because you've already done that when it was first installed.
Exactly.
Yep. And now what's this one? This is again another Digitrip 520. That's the trip unit, which is all inside the breaker. And I think, correct me if I'm wrong, but I believe this dotted line that's right here is the circuit breaker, basically.
Yes. So So the circuit breaker has its CTs on the three-phase conductors. There's actually no CT now on the neutral conductor or that ground path, but we have that zero sequence CT at the bottom that's wrapped around the neutral in all three phases, like we saw in the diagram earlier.
Okay.
And that is again feeding into the trip unit and ultimately feeding into the same location in the trip unit.
Okay. So you're saying that this down here is a zero sequence CT that's around these four conductors, right? And then the output of this goes into the circuit breaker trip unit, and
Mhm.
and it passes. There's another 10-to-1 ratio, so we're stepping it up again. And I would assume then that the size of this CT, the ratio of that CT, the accuracy of that CT is all going to be dictated by the manufacturer to tell you what you need to put there. Because if I've got another ratio over here, I've got to know. I've got to specify really what CT you're going to have there is, but that would probably be supplied by the gear, which if it's our gear, we would have put all this together so it would work.
Right, right. Yeah, it's all going to be specified, as well as ensuring that you don't have CT saturation,
Right.
which, right, we already consider that also. Now, a little different here for those on the call that ultimately work in that utility world and the higher voltages. When you start talking about ground fault protection, you have to really be concerned about that saturation. And once you start working with relays, you have to be concerned about all the burdens that are going to occur. And there's a lot of calculations that go into how do you choose that right CT.
Yeah. Yeah, and then but now on some of these, like for example, I know like I've done burden calculations, which basically the burden calculation for a CT, you're looking at all of the different devices you have in that CT circuit because it's only going to be able to handle so much load in that CT circuit. I've seen that. I've done those calculations for like some relaying, but mostly like for metering, and there's other things that are in there. But on some of these, like this is probably the only load, right? So
Mhm.
you probably you're more than likely not having to worry about a lot of different things hung off of this zero sequence CT. If it was a phase CT, you might have various relays doing 50, 51, 49, all those different types of relays giving you different functions that you have to think about. This one here is going straight into the breaker, so I don't necessarily have to worry about that, but you make a good point with regard to saturation, knowing what is the expected fault current value, because if it's really high, which these zero sequence wouldn't be really high, right? It'll be a low number because it's not going to be like 20,000 amps. It'll be a smaller number because it'll be a differential. Okay. But I guess it could be pretty doggone high, couldn't it?
It could be depending on where you are in the system, right?
That's true.
That's where it matters. So yeah, with the low voltage breakers, like you said, it's going to go back to the manufacturer. It's going to be specified when you choose the breaker based on its size, based on the short circuit rating or the interrupting rating of the devices in the switchgear, right? All that's going to feed into and say, you need this CT and here's the specs
That's right.
for that.
Yep. So CT selection's important. Following the manufacturer's instructions, make sure it's paired up correctly with the trip units that you're using. So, and in some cases, the manufacturer will put their CTs in there in the gear, so to speak, and we'll make sure that it's all matched. But if you're retrofitting or you're doing something in the field separately, you got to think about the burden, how many different relays you're hanging off of this thing. You got to think about the CT ratio. You got to make sure it's either a relaying class CT as opposed to a metering class CT from an accuracy, and that goes to saturation on how much current you're expecting to see. Good discussion there. Now this is the residual. So this one was who was it gave us the thumbs up on the residual? I think that was Douglas, right? Douglas Strang. He's like, I love the residual over zero sequence. Um, and so this one here, you're doing the typically though. I mean, I'm trying to think if we do that in our breakers. We probably wouldn't. I mean, maybe in some breakers we do a residual because you'd have to have the neutral. So if you have to have a 4-pole breaker, and
Right.
I could do the residual in my breaker if I have a CT around the neutral and the 3 hots internally to the brain of the electronic trip unit. I could give myself and do my calculation from a ground fault perspective.
Right. Yeah. And actually, when we talk about like Eaton's Magnum DS,
Hmm.
if you purchase a 4-pole breaker, you can do residual grounding where, yes, every pole of the breaker, all 4 of them would have the sensors, right? The
Right.
CTs installed into it, and it's all wired, it's all internal to the breaker. You don't have to worry about all that external wiring if you do that.
That's right. That's right. Yeah, and that's very convenient. Very convenient.
hmm but ultimately, the math is the same. It's just doing a summation of all of the currents, and it should add up to be 0.
That's right. I'm liking it. And then this is again your residual concept. So your CO relays can now a CO relay. Now you're talking relays, which relays really would be in a medium voltage type of application, right? I mean, I've seen some relays at 480 volt lineups of switchgear, but that's a pretty sophisticated system. You might see that in a heavy industrial, but you're not going to see that
Right.
in a commercial building, though.
No, not typically, but I it's a good note to say, this doesn't just apply to the low voltage system. I mean, what we're talking about with the
That's right.
ground fault protection, it applies across the board. And I mean, when did the CO really come out? I don't remember. I should have looked that up before we got into this presentation, I guess. But I'm going to say it was decades ago
Oh yeah.
that easily, right?
Yep.
That relay came out. We're using the same fundamental concepts for protection that we've been using for decades.
That's exactly
Um,
right.
it,
Physics. It's
it, it
all
works.
physics. It's all physics, and physics doesn't change. And so this is your this is your residual 3-wire concept. That's like a CO relay, and this would be what we do today in the Digitrip. And you're noticing, and it's exactly what I just said, right? So well, you do have this in the neutral here, right?
Right. So if you're doing residual and you have a 3-pole breaker, but it's a 4-wire system, that's really what we're talking about here. You have to have those CTs, the sensors on all 4 wires.
Right.
They're going to go to the trip unit, and the trip unit is going to do the summation.
Yep. Yeah, that's exactly right. Now, how would you and now this is the breaker, right? So here's your breaker. This is exactly what we were just talking about. There's your circuit breaker, and now you have a 4-pole circuit breaker, and that CT, this CT, and this CT are all in one. And this is where I would hear arguments that look, testing this circuit breaker, it was tested, and let's say it's a molded case circuit breaker, because remember we're talking 1,000 amps and above. I can have a 1,000-amp molded case circuit breaker. This circuit breaker, you're not going to take it apart. Right? It was tested at the factory. There's a test report that you can get with it. We tested the ground fault. We test everything on it. So if there's a miswiring, it's going to be, and it's mounted to the bus. So I've heard people say, why would I test this for ground fault if it's a molded case circuit breaker? I know that thing is, I'm doing this basically the same test that was done at the factory. And true, you're not going to be testing the polarity, but you would be testing to make sure that the breaker wasn't damaged in shipment, wasn't damaged in as it sat on the job site before it was actually installed, and all of that, all of those good things. You would be testing its full functionality, doing primary current injection testing, tests everything, right? And and so that would be my argument that it's not for nothing Because I've heard people say, well, you're just making me test this thing. It was tested at the factory. I got a test report right here, and it says it was working when it left the factory, 6 months ago, and now I'm installing it, and you're telling me I got to test it again. But you don't know whatever happened to that breaker in those 6 months. So, I mean, it's just a level of insurance.
Yeah, I mean, I'll give you my thought on it from an analogy perspective. You got to go buy a brand new big screen TV. Are you going to go to the store and the store is going to tell you there's absolutely no returns of this TV? You walk out the door with it, right? We tested it at the factory. It worked, right? We got the tested by number, 17, right? Um, are you going to walk out the door with that TV if they tell you you can't bring it back if it doesn't work? Not a chance, right?
Yeah.
And that's because, like you said, things happen
Yep.
during shipment.
That's right.
I always tell everybody, I'm like, when I come to a site and do training, it never fails. It happens a few times a year. I bring a piece of test equipment with me. I bring a demo with me, and it worked here in Warrendale.
Right.
When I'm here in the office, it worked perfectly. It tested with my computer. I now drive a few states down the road, set it on the customer's table, and I hit the test button, and it doesn't work.
Yep.
All right, something shook loose during shipment, during that travel. It happens.
Yeah.
And ultimately, this is important. We want to make sure that this system works when
Hmm.
it's at site.
Now, well, how you would probably now testing a breaker like this, because it's nice, it's all contained. If you had your test unit here, you could connect a lead to here, right, and then connect the lead, say to here, and when you inject current down through here, it goes back to this unit. It doesn't return back through this, like say you did, because it's a 3 phases, right? So you have 3 phases going this way, 1, 2, 3 coming this way, and then you would connect the current back through. And basically what you're doing is you're bypassing this with your current. So this CT, and this CT, and this CT sees current flowing this way. This guy doesn't see current flowing that way, or not the same amount of current. And the device, the brain in here, should say, I've got a problem, right? Because now I've got current flowing through here, but not back through the neutral. Now you could also, and I'm not sure if this is how that system works, but you could probably dictate how much current flows through here and only put a portion of that through the neutral to give you a differential, and test the pickup points, right?
Mhm. Yeah, I mean, typically we wouldn't even inject current into all 3 phases at the same time. We
Okay.
would typically you would just inject because most of the test sets are going to be a single phase output for the primary current. Um, you're going to inject that current into phase A. It doesn't go back through the neutral sensor the opposite direction.
Right.
That's a ground fault. It should trip. Then you would move the leads to phase B, do the same, it should trip. Move them to phase C, it should trip. Between those, though, you may decide to run it through that neutral sensor the opposite direction. And phase A and neutral are the same, but opposite directions. That should
uh
be a no
oh
ultimately.
yeah, so there's a trip and a no trip, so you've got to verify that imbalances won't trip the breaker, right?
Yes, yeah, yeah. We want to make sure all the polarities are correct because, I mean, just confirming it tripped didn't actually confirm all of your CT hookups. So think about this. You injected current through phase A, right?
Right.
And it didn't go back through the neutral conductor, the neutral CT, the opposite direction. That would be a trip. We'd be happy with that. But you didn't actually confirm the neutral CT was connected properly. So that's why you need to run the current back through it the opposite direction and make sure that it doesn't trip. If you run it through the same direction, it should still trip.
Now,
So we got to confirm the polarity.
when you say run it through, well, are you talking about, so in the first test you're coming this way? Are you talking about phase A pushing current back through that way?
No. So I'm saying phase A down,
Yeah,
like through. So we want to do just phase A current going through. That should be a trip.
right.
When we then put the neutral into it, we should have the arrow pointing up on the neutral.
Okay.
That should be no trip. If it trips, that means the wires on that neutral sensor are flipped on the secondary side.
Oh, okay. So,
Right? We need to confirm that.
when you're going through the neutral this way, are you also putting current through phase A?
Yes.
Okay, so you're basically jumpering this right here,
Mhm.
and you're sending current down that way and back up through that neutral, and then that should not trip because both of those CTs are seeing the same thing. And that confirms that this CT is correct, whether it's in the breaker or outside of the circuit breaker, it's the same type of test.
Yes.
Perfect.
Exactly.
Okay. You know what?
And then so what is that? That's 2, maybe 3 tests
Yep.
for phase A. And then we're going to do that for phase B. Then we're going to do that for phase C.
Right. Because you've confirmed that this CT is the right direction this CT is the right direction in relation to this one. And then you're going to set it all back up again. You're going to run this current through there. And then you're going to do this and run this current up through there. And now you know that this CT is in the right phase direction as with respect to that CT. And then you're going to do phase C the same way.
Yeah, because if you think about your phase protection, CT polarity doesn't actually matter on overcurrent.
That's right.
Right? But in this instance, we're confirming we have no ground current by using all of our CTs, we need to confirm all of them are wired to the proper polarity.
That's right. And that's how you do that is you're physically injecting current down through this one and then back up through that one. And now you know that it should not trip because this current and this current will be the same if they're both the right polarity. I love it. Okay, I get it now. And that would go the same. That would be the same for this. The CT's on the outside, but you're going to inject current down this way, and you're going to put a jumper in there, and you're going to have that current come up this way. That makes sure that this CT and that CT have the right polarity. The same with this one. The same with that one. And regardless of the application, and then you're going to be doing if it's this, you're doing the same thing. If it's this one, you're doing similar. You're doing the same on all of these, really. I mean, outside of the zero sequence, right? I mean,
right. Yeah, the zero sequence, the polarity doesn't matter. It's not as important, but with the zero sequence, think of it this way. So, Tom, I go to the back of the switchgear, and where does all the busbark run, right? And especially now we have all these service entrances that we like to put barriers up on, so you separate your line side from your load side. How do you know where that neutral bus really runs in the switchgear? Where the phase A, B, and C actually are bolted together in the switchgear. It's hard to trace out and follow the directions of everything, right?
That's right.
So we're still confirming again that all the connections work out to be the right direction.
And that's why it's really important from a person who's doing it. If you look at the latest version of the National Electrical Code, we said a qualified person because it's more than just a qualified person on this relay. If you're looking at a lineup of switchgear, and whether it's my switchgear or one of my competitors' switchgears, which I don't think anybody would ever have to test theirs because nobody installs that stuff. Everybody installs Eaton equipment, right? So, but you have to know the equipment itself to know which buses are A, B, and C, how you're going to clamp on, what you need to turn off and isolate, all that good stuff. So it's more than just knowing the breaker or the fusible switch. You got to know the whole assembly.
Absolutely. I mean, I'll tell you a story. Years ago, I was involved in a job, and a employee of our company went out. I won't say who the manufacturer of the switchgear was. Don't
Hmm.
give them a bad name, right? But they got called out that they're having these issues with ultimately the coordination of the system. So the employee goes out and starts to really test the coordination and goes through the transfer scheme that was on the switchgear, double-ended main time main, right?
Hmm.
And finds out the transfer scheme's not quite working the way he thought it should ultimately. So dives into it a little bit more and says, okay, I got to take your switchgear and make it electrically safe on half the switchgear. And he does this and he realizes there's a motor behind him that's running. And he's looking at the drawings and this motor's running, but this motor's fed from the side of the switchgear he just turned off. And he's looking at this, kind of like, okay, what's going on here? Maybe someone wired it to the wrong side of the switchgear, right? And he starts diving into this and finds out that the manufacturer had actually bussed around the tiebreaker
Oh, wow.
in the back of the switchgear, had actually built the bus and bypassed the tiebreaker completely.
Oh,
Now you would say that can't happen, and how did it happen? And the switchgear was in service for a few years before anybody even figured this out. That's why this testing is so important, to
yeah.
make sure you have, like you said, qualified individuals that don't just understand the breaker, but the system overall, all the different components. Do those tests from the start to confirm
Yeah.
that mistakes weren't made in the design process, in the manufacturing process, shipping a switchgear. I'm a little rusty on this, Tom, how many sections of switchgear we can ship at one time, all bolted together.
Yeah. Yeah.
But a
Yeah.
lot of
Yeah.
switchgear, right, comes in pieces that are actually bolted together in the field, right?
That's
Not
right.
by the manufacturer, so mistakes happen.
Yep, and we got George Corey online. He just showed up, which or a little bit ago he showed up. So thanks for joining us, George. Now you sent me over a few pictures.
Yeah, yeah. I mean, so talking about all that bus work and what's going on here. So that's just a low voltage uh, section of a switchgear. The transformers on the right. So we have the bus work coming in, and it's connecting to the bus work to the switchgear. Phase A is at the very top, B, and then C. And what's interesting is we have that neutral bus bar that you see in front of you, near the bottom of the picture. Below that, we actually even have ground, and there's actually a piece of bus bar. It's almost impossible to take a picture of without getting in the switchgear. To the left, behind the barrier, is actually where the neutral to ground bond is inside the switchgear.
Ah,
As well as, you're going to love this, if you looked on the side of the transformer, there's the grounding strap on there too. So in this one section of switchgear, we actually grounded it twice, the neutral to ground bond.
wow, wow,
Yeah.
interesting.
So weird things happen.
Yeah, and you've got to be mindful of those bonds that are in there because you're going to have to work around those and figure out how that impacts your testing, right?
Absolutely. Absolutely. What bus work do you take apart to make your test?
That's right.
This is actually the other end of that exact same switchgear, and right where the one hinges at near the top of the picture, Tom, where the white sticker is on the bus bar. That's the actual neutral to ground bond inside of
Ah,
the switchgear.
okay. So,
All right. So the right and the left of the switchgear are actually different.
oh, wow. So you really got to know what you're looking at to understand what that linkage is, what this bar right here. It says neutral disk, but you could have two of these in there, right?
You could, absolutely.
Wow. And then looking to see, are you now this is a close up.
That's close up of the right hand side coming off the transformer. So you got phase A, B, C, front to back. There's your neutral connection, and the ground is not actually in the picture. I don't think.
Okay,
So you
so
can see it.
so the one closest to us here is A.
No, that's neutral.
I was gonna say, yeah, because these three look like A, B, and C, and so it's A, B, C, and then neutral.
Correct.
Should that be late? Now that looks. Shouldn't these be labeled A, B, and C somewhere here?
Um, they typically are. It just might be near the bottom
Okay.
underneath all the bus, so you might not be able to see it.
All right. Gotcha. Gotcha.
But talking about things that happen during shipping, it's always dry when the equipment leaves the manufacturer and ships to site, right? We never have any rain or high humidity that might make those labels fall off or become unreadable,
Right. Right.
right? That never happens.
No. 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 We just ship those out separately. All right. So there's your.
Yeah, there's the view. I tried. It's kind of hard to see. The bus bar closest to us that's vertical goes over to the left, and where you see the two bolts, it then makes a turn down, and that's actually your ground bond for the
Okay.
neutral.
Yeah. Oh, Tamaki says there's a code requirement about phase arrangement. There very well may be, Tamaki. Yeah.
I know there are manufacturing standards, ANSI standards around that. I think though it uses that word typical here and there. So
Yeah.
there are times when we flip them ultimately.
Yeah.
So what you're looking at here, Tom, is actually a pad mounted transformer ultimately. And you see that neutral is on the far left. Yep, right there with that green cable. That's the bond that's bonding it to ground.
Yeah.
Ultimately, there's a bus bar at the very bottom. I think it's in the picture.
Yeah. Right
Um,
here. Right here.
yep, right
Yeah.
there.
Yeah. That's pretty cool. And those are your cable limiters. That's protecting the cable. And I have a video of him installing those, which we should do a program on cable limiters too one day. So you've got to understand this equipment. You've got to understand everything you just explained about all of the jumpers. What is A, what is B, what is C, because you're going to be clamping and clipping and then trying to isolate things so that, to your point, you're not getting currents flowing out of where you think they're flowing. It can get complicated pretty fast, so it's not left to somebody who doesn't do this routinely. Especially if it's different manufacturers of equipment, things are going to be arranged differently based upon the manufacturer. So you've got to understand the equipment in addition to the technology that you're using to run the tests.
Yes, and one of those other interesting things to be aware of is you're injecting lower currents, right? We've been talking about the 1200,000 amp
Yep.
ground fault level, but we need to test high enough that we make sure that we are above that threshold, right? So generally, about 125% of pickup is what you're looking for, but if you're just injecting current through like a zero sequence and one phase of a larger breaker, do you actually have enough ampacity to self power the trip unit? You might
Ah.
not in some cases, right? Because
Yeah.
there's no actual power coming off of that neutral or zero sequence CT circuit. It's coming off the phase sensors, right? So now we need to make sure I'm testing a high enough current that I can, have my trip, guaranteed of that. But now I need to plan for how do I actually power the trip unit so that I can see all this happening. maybe I need to have more current injected into the phase to take care of that. Maybe I need to have an auxiliary power supply into my trip unit to make it run and
Yeah.
show all the.
I had a question one time from a customer of ours who had one of our larger breakers on a circuit that had very, very low current. Okay. So it was a very large breaker. It had very low current. And his concern was that, and it, everything was sized correctly. But his concern was that typically there's not drawing enough current to your point that it's actually enough that the trip unit is like awake, right? Because we're getting the power off of that current that's flowing through there. And his question was, will your breaker actually function and work and trip? And the response to that was that when you have a fault, you'll have enough fault current that it will drive that trip unit to open and do its job. But you make a very good point and a very interesting point that we need to put enough current through here to operate and so that these devices get their power so they can actually function and do what they're supposed to do in the test sequence.
Right. Because the test sequence, we're only injecting one phase,
Right.
right? So we don't have all three CTs adding together to give us that power.
That's
So,
right. That's a very good point.
So, the other thing, sorry, I apologize. I don't know if you can hear in the background, there's weather alert coming through the building right now.
Oh, is that right?
because we got some severe storms here. I was wondering why the light was blinking behind me. The other thing that I think is important, because I know we've been asked, we're at 2 hours now, right? Almost.
Yeah, I know. I'm
amazing.
like, holy cow.
It's awesome. Loving this. So talking about how complex this can be, I know I sent you in that one slideshow I sent you. What happens if you have like a residual connection?
Yep.
It's slide 50 in my slideshow, Tom. And you have that main tie situation occur, right? So 3 mains and 3 ties. That is 18 tests that you're going to perform on this ground fault system. I mean, it's not that it's a necessarily a difficult topic to understand ultimately, but there's a lot of details to it, right?
Yeah.
So yep, right there, 18 different tests to perform. So this is identifying the position of your breakers. Are they open or closed? That's what the first 2 columns are: M1, M2, M3, T1, T2, T3. What you're going to inject current onto, so A1 and N1, so that's those breakers, those buses, and then where you need the jumpers to have the current flow back through the sensor properly, right?
Mm-hmm.
And what your expected result would actually look like if it's a trip or no trip. And in this case, with so many mains and ties, what breakers do we expect to trip?
Right, and this is the basic arrangement for that scenario, right?
Absolutely, and it's kind of hard to. I know it's small, right? So it's hard to zoom in, but that diagram there, where there's a red on the diagram, what that's showing you the different connection points ultimately that you would have. So when we get into these more complex systems, we have to make sure that we plan this out, so that we test all the functionality of it. And also we're trying to limit how many times do I need to move all these cables.
Yeah, because like you say, you take a lineup like this, which is very complicated, and you don't want the customers to be terminating all of their feeds and that, because you're going to have to disconnect all of that anyway. And you're basically being surgical about it to figure out all of these test points, every source, and how you're going to put your sources are, where your jumpers are going to be, and then what the test results need to be. So you're going to have 18 tests on this main tie, or main tie, which is basically what you got going on here. But then, like on this one here, you've got 3, but if you've got zone selective interlocking and all this other good stuff, you've got to think about too, because there's jumpers associated with ZSI. And if you're going to test CSI, like for example 24087, if you're employing zone selective interlocking to meet the requirements of 24087, you're in here doing ground fault protection already. You know you have zone selective interlocking in here. You've got to make sure that you've got that taken care of, because if you're going to test the ground fault and you're actually tripping on zone selective interlocking because of how you've got it set up, it's confusing.
It really is. So, I mean, that's where, as you stated earlier, it really takes that qualified, knowledgeable person to understand all these various systems that are interacting and how do you deal with them? How do you ensure you're tripping on the functions you want?
Right.
Um, so it goes back to I get asked that question a lot, I use Schweitzer relays, right? So a very advanced relay that a lot of people use on utility systems. Can you just come and show me how to test the Schweitzer relay? Well, no, I can't, right? Because there's all those unique things about a Schweitzer. There's the software, the communication, right? And then how many functions does a Schweitzer relay hold, right?
Yeah.
A few hundred, right? At least maybe thousands. Same here in the switch gears. We add more and more protection features. It really is becoming a little more complicated from the testing standpoint to know, okay, what function am I testing and how do I eliminate everything else that may appear to be the right result, but it happened the wrong way.
Melvo Rubio in the house. Thanks for joining us. Excellent. So main time main situations, you've got to be careful about what is you're going to open up all your feeder breakers. Are you going to open up the tie breaker? You're going to keep it closed? Or do you have to do the test with it open and one with it closed?
Well, that's exactly what you're going to do. You're going to run tests with your two mains closed and your ties open. You're going to run tests with one main and the tie, and then test with your other main and your tie, because you want to confirm. And in this instance, with the residual connection, right, we have now multiple sensors or multiple CTs feeding back into those trip units, right,
Yep.
to make that work ultimately. And we're going to test the coordination of the system. So I'm going to see that happening also to ensure that the tiebreaker and the main breaker are actually coordinated properly from a ground fault perspective.
Right. So you're going to take a one line diagram like that, and then you're going to walk over to a piece of equipment that looks like this, and you're going to be trying to figure out what am I clamping onto, and what do I need to isolate and all that. So you've got to make heads and tails out of both the one line and the actual physical structure to get your testing done.
And Tom, I'll demonstrate what that looks like. Normally, it's a little bit of this head scratching, right? Trying
Yeah.
to figure it out, right?
Right.
And you're pulling out drawings, and generally, when you see individuals testing this, that first day they generally have sets of drawings laid across the table,
Yeah.
right, with things highlighted and colored to show everything that's happening and figure out what does this test plan really look like in the gear.
That's exactly right. And that's I think that's a part of the challenge with all of this. So, you can go from a very simple single breaker installation, say a main and a panel board, but when you start getting into the big stuff, the switch gear or switchboards, it gets much more complicated. And then when you're dealing with double-ended switch gear and different types of bonding and grounding and different types of whether it's zero sequence or all of that good stuff that we just talked about earlier, it will add to the complexity. And so the qualified individual is really critical at that point. And then you're going to want to get the 24087 and 24067 done at the same time.
Mm-hmm. Yeah,
And
and I'll go back to I think I made this point last time I was here with you, and I just want to come back to it a little bit. You know, when I first came into this industry and I got hired with Eaton, and right, I'm going through what does Eaton do? Huge manufacturer of equipment.
Mhm.
I'm imagining our Arden plant, our Sumter plant, right? Asheville, all the places we manufacture this equipment, and I'm picturing Ford, you know, processes where you have these product lines, right? And the switchgear just moves down this rolling conveyor and parts are put on because a switchgear is a switchgear. A switchboard is a switchboard, right?
Yeah.
But that's really not how it is. If you go to our factories and you walk the floor, you find out there's no conveyor belts, there's no moving lines of equipment because every piece of equipment that's manufactured is custom.
Yeah.
Every switchgear looks a little different, has a
That's right.
little different functionality, and those details are important in what we're discussing here.
Yeah, that's exactly right. Now, Tamaki's asking for a code reference, and I'm not sure what code reference that you're looking for, Tamaki. Like, you let me know in reference to what. NEC 2020, I forgot the article number. 24087 and 24067 is for arc reduction technologies. 23095 is your ground fault protection of equipment. So, and that's for the services. But remember, when it comes to service equipment, when it comes to 1000 amps and above, you have 23095, you have 210, which is your branch circuits. There is a ground fault in 210.13, and then in feeders. Oh wait,
he's looking for the layout of the bus work. I think.
Oh, layout of the bus work. I'm not sure, to tell you the truth. We're talking, I think when we were talking phase A, B, and C, I am not sure of that code reference. 408.3E. Thank you, Joe Bellantoni. Look at that. See? This is, you know what we call this? Cross-pollination. It's like bumblebees. This is like a beehive. So let's take a look at 408.3E. 408.3 is support and arrangement of bus bars. Yeah, that would make sense. Bus arrangement. All right, we got AC bus arrangements. You have alternating current. Phase arrangements on three-phase buses shall be ABC from front to back, top to bottom, or left to right, as viewed from the front of the switchboard, switchgear, or panel board. The B phase shall be that phase having the higher voltage to ground on three-phase 4-wire delta connected systems. Other bus bar arrangements shall be permitted for additions to existing installations and shall be marked. So this helps in the testing, helps the electrical worker and all that good stuff. So thank you, Bellantoni, Mr. Giuseppe. And he is here from the beginning and he is here in the end. And Tamaki, what time is it over in Japan right now? It's probably in the morning. And did you just wake up? Because you're sharp as a knife.
Teamwork.
Yeah,
this is teamwork.
This really is, and that's what I love about this. And what it really shows is not one individual knows everything, except for Joe Bellantoni and a guy like Randy Jackson. You get all these people. They and together we know and we can figure out a lot of stuff. So. And I it's almost bedtime for me and Tamaki. It's I guess morning. They're probably over there sipping a cup of coffee. And you ever been to Japan, Michael?
I have not, and I was trying to remember. Is it morning of yesterday?
No, it's tomorrow.
Today or tomorrow? It's tomorrow already.
Yes,
wow.
Because Tamaki is going to. It's 8:00 in the morning. So Tamaki, you've got to tell us what the lottery numbers are for today. Because it's tomorrow. So for tomorrow, so that we can hit the lottery, and then we'll come pick you up, and we will go have a blast on. I don't know. Maybe we'll go. We'll just go hopping around the world. We're going to hit so much money because Tamaki's going to tell us what the lottery numbers are.
Hey Tom, I think we've missed it for tonight. Isn't the lottery at 7:00? It's 7:08. I think we missed it. We'll have to work another day.
Yeah, we'll have to work. We'll have to work another day. Awesome. So 408.3. So
love it.
What else? David. All right. Excellent. Well, I think we covered testing of the complicated systems. We know we're going around those CTs. We talked about making sure the polarity of the CTs and jumpering and why the jumpers are important. The tripping and no tripping. The no tripping is there to make sure that the polarity on those neutral CTs with regard to in respect to the phase CTs are correct. Um, what else? Oh yeah, and this is again to reinforce that, this is your what do you call it? This is how we already talked about this. There's you got your A and B. You're going to be doing A and B. That shouldn't trip either, right? Yeah, no. That's a no trip test. So you've also got to do relationship with each other, not just the neutral.
Hmm.
That's a good point.
Yes.
That's a really good point.
If you're, well, yeah, and that's because this is in a residual connection, right? So in
Yeah.
residual, we have to be able to sum up in the sensors or the CTs that we have available to us. It has to equal zero. So yeah, no trip in this instance because we don't actually have a neutral CT.
That's exactly right. So what we have to do now, let me just do this. Let's just do this real quick. Okay. Tamaki is in Kanagawa, Japan. So this is basically what all that looks like. Wow. Look at
Mm.
that, huh? And let's see where whoa, I don't want to do that. Oh, and I just did it. Whatever it was that I did it. Let's take a look. Where's Kanagawa? Kanagawa. There it is, right there. So you're south of. I guess it's south. You're in that blue dot, so that would be there's Tokyo. That's where I was at. I was in Tokyo, so I see where that's at. So it looks like they got a nice big Ferris wheel, and Tamaki is probably deployed there back for 11 months. Oh, so Joe Bellantoni was deployed there for 11 months in '87.
Mm.
Excellent, excellent. So there it is. Look at that. Kanagawa. Kanagawa. I hope I said that right. Kanagawa. All right. Well, that's Kanagawa. That's where Tamaki's at. And we got to, you know what we're going to have to do is we're going to have to get some pictures of Kanagawa. So we're one of our programs, we're going to get Tamaki online and we'll do a review of Kanagawa.
Well, I'm thinking, Tom. We travel there, and the three of us, two of us and Tamaki, we could do a tech talk live from Japan.
I'd love to. I'd love to. It's beautiful over there. Absolutely gorgeous over there. All right, so we covered a lot of material. I think we covered a lot from the historical perspective, from the code perspective, testing. We went through different test configurations. So I think we have the understanding of the complexity of the nature, and then what the fundamental principles are. Testing those polarities, and we test that going back and forth between A and B, B and C, and neutral. We have trip and no trip tests. This is all good stuff. And Felix Sandoval, thanks for hanging in there. And we, Felix, we got Electrical Safety Month is in May, and I'm filling out the program. I need everybody to go out and take a look because I'm continuously updating the program. And if you go to thomasdimitrovich.com, you will get to go to calendar of events, thomasdimitrovich.com, calendar of events, and we're going to start next week. You go to May. We're going to start next week with GFCIs, myself and David Smith. Then we're going to hit AFCIs on the 6th. We're going to hit personal protective equipment on the 11th. We got arc resistant equipment on the 13th. Life safety requirements article 700 on the 25th. One of these days, you and I are going to do, we said arc flash, right? We're going to do Maybe we talk about arc flash calculations and things like that, maybe safety by design or whatnot. But I have a special guest that I met last night who is going to bring, in my opinion, David, Michael, and David, in my opinion, one of the most important things from electrical safe work practices. It is the topic that we're going to cover, which I'm going to figure out when it's going to be. I got to communicate with him. We're going to come up with a title, but it, in my opinion, is one of the most important aspects of electrical safe work practices. More important than PPE, more important than anything else. And it's going to be a really good discussion. He is out of Chicago. I met him last night, and again, and he's a I'm not going to give anything else away, but it's going to be a very good discussion. But I'll end up putting it on here, and I will somehow. I got to figure out the good title so that everybody understands. In my opinion, it is going to be one of the most critical discussions from electrical safety perspective. So, we're going to be filling this out, and I want to fill in more days. So, if anybody out there wants a discussion on a specific topic, please let me know. All right, so check out that, and Michael, we kicked butt, buddy. I mean, we got through a lot of stuff. We hopefully shared a lot of information, and I don't know. What do you think?
I think it's amazing. I mean, when you first started this, Tom, how long were your first presentations? I mean,
I don't know. You know what? Here's the thing. I tried to do 15 minutes and they were 30 minutes. I went from 30 minutes to an hour. And I had Nihad El Sharif saying, well, I called them 15-minute tech talks. And then I said, well, 30-minute tech talks. Actually, I tried 10 minutes. And then finally, we just went to 2-hour programs. And so sometimes we're shorter, sometimes we're longer. I don't know.
yeah, but I was going to say, that's the thing. I think, Tom, when we talk about electrical installations, we talk about safety. There's just so much that we need to know, right? I
Yeah.
mean, it doesn't matter if you're a electrician, a
Hmm.
consultant engineer, you're a facility manager, maintenance personnel, right? There's just so much in today's equipment in our facilities. Where do you gain all that knowledge? And I always thank you every time I get an opportunity, Tom, for
I appreciate
putting
it.
these on and having me be here with you and hopefully adding to the conversation a little bit.
Absolutely.
I appreciate that, and I love these events. Honestly, I told a fellow Eaton employee about these events that has like 35 years of experience, and
Wow.
he watched one of these with you. And I forget which one it was. I think it was on panel boards, actually, is what it
Ah,
was. What a panel board was. And he said, I thought the box was a panel board. He's like, I honestly didn't
yeah.
know that after all these years. So, I think these events are great, and just passing this knowledge, sharing this knowledge is
Yeah.
just absolutely awesome that we can do this, even during COVID time.
Oh yeah, yeah,
So,
yeah. And then we're going to continue on. So I really appreciate you taking the time out of your day. This is all extracurricular, brother. So I appreciate you sharing your knowledge, and you're always welcome. And we had Steve Froming in the house, and we're from Wisconsin, Tamaki. We got Holmes Law and all this good stuff. So thanks everybody for tuning in. Thank you, Michael, for sharing your knowledge and. Remember, Electrical Safety Month's coming up, and we're going to have a lot of different programs, a lot of different opportunities to talk about electrical safe work practices and electrical safety. So we're all going to go home at the
one
end of the day. Yeah.
and one more item, Tom. You gave me the opportunity, and I've completely forgotten to do it because I'm so focused on this. There's a website, right, where there can be more training.
Yes.
Oh, it's scrolling right now, eaton.com/electrical worker training. And what's our code, Tom? There's a promo code.
Eaton Tech Talk. So you come over here and you say, look, I want either in-person instruction, virtual simulations, and let's say you want to get some in-person because always, getting Michael out there in the field is great. And you say, I want some hands-on. I want to get into registration, contact form, right? So
Yep.
basically tell them what you want, whether you want transfer switches, basic electrical testing, all this good stuff. You pick what you're looking for, and check, money, MasterCard, all that good stuff. But if you have a code, this is where you would put Eaton Tech Talk, right?
Well, yes, and I want to see, Tom. We're doing this live, so
Yeah.
I hope this works. Scroll back down. I think there was a box. How did you hear about this? How did you hear about
Right
Eaton's
here.
training? Does it work? Is Eaton Tech Talk in there yet? It's
No.
not there. It will be. I promise you. The next time I'm here, it is going to be in that form, so that we definitely know. Even if you forgot the promo code, we want to give you that 10% discount, no doubt.
You are the man, and I am not a robot. All right, so excellent. I really appreciate that, and I know everybody out there appreciates that. So just trying to help people get educated. So the smarter we are, the smarter we work, the more we go home safely. So thank you very much for that.
All right, no problem.
All righty, everybody out there in YouTube land, LinkedIn land, Facebook land, thanks for hanging in there for this session, for this evening with us. And remember, it's up there forever. Check out my YouTube site, log into it, or not log into it, subscribe to it, hit the thumbs up, hit the thumbs down. I don't care. Give me that feedback, because that's what we want. And we will see you on Tuesday of next week. Okay, so Holmes Law, look at this. This is cross-pollination going on, 408.3E. And they're talking about 408.3E. I just want to just double check.
That's the phasing.
Yeah, and it was. And that was the 2020 code. 2020 code was the 408.3E, and it was changed. So I don't know about the previous versions, but that was the phasing. So all right, everybody. I got to go upstairs, and Michael, you got to go home, buddy.
Well, one of these fine hours,
Yeah,
we got to keep it going.
that's exactly right. All right, so I'm going to just fade this out and thank everybody out there. Thanks for what you do for the electrical industry. Thanks for what you do for electrical safety. Stay safe and please stay healthy. And until Tuesday of next week, we will see you guys and everybody later. Thank you very much for hanging in there. And thank you, Michael, again. I really appreciate it.